Now let's quickly look at the real gas molecules as compared to the ideal gases. Now these ones would have some odd shapes that can affect their properties. For example, water vapor is a gas, has got shapes, those molecules have got some odd shapes that affect their properties.
And of course, a few lessons ago we did talk about that and how it's a dipole because there's a separation of the charges and so on. Now all of that would, I mean, obviously if it's a dipole, there are cohesive forces.
Exactly, there
so
would be
we
forces
can't get away
existing
from that.
between those molecules.
Yeah. So we'd expect that to behave in a fairly non-ideal way.
Exactly.
Okay.
Now, and these molecules would occupy volume.
We can't really ignore it, can we?
Exactly. They would occupy volume, and the molecular volume becomes noticeable at low temperatures when molecules slow down. Now, at low temperatures, remember that is when the kinetic energy of the particles or molecules is low, so they move very slowly. These molecules do exert forces on each other, especially at low temperatures and high pressures.
Again, where these molecules are going to be close together, eh?
Exactly. So the cohesive forces becomes very strong between them.
Okay.
And lastly, these particles or molecules will lose energy when they collide with each other and the walls of their container. So as wherever they are, as they bump against the walls of the container, as they bump against each other, they are going to lose energy. In other words, the collision between these molecules and between the molecules and the walls of the container are not completely elastic.
Okay, so we can't really ignore them, but we're going to have a good try at it while we deal with our ideal gases. Now, Tanika, you will remember that when we took the little syringe and applied some force, in other words, increased the pressure of the gas, and I held my thumb over there, then as the volume decreased, so the pressure increased here. And I could tell that the pressure increased because when I took my thumb away, I would hear the gas rushing out, out it would go. So in other words, as the volume decreases, the pressure of the gas would increase. So we've got what is called an inverse relationship here. And we can write this as P. In fact, we can't be absolutely sure that just from this discussion that it is inversely proportional, but we can let everybody into a secret that in fact it is. And that is shown using the Boyle's law, or Robert Boyle's method of showing this relationship, this inverse relationship between pressure of a gas and its volume. So what this says is that if I double the volume, in other words, take the plunger out and double the volume, then the pressure will halve, because the pressure will now be proportional to 1 over 2V. And so it will have halved. And I think we can appreciate that because the same mass of gas, and by the way, we have got the mass of gas is constant. So we're taking a fixed mass of gas. In other words, we could also say the number of moles
of the gas there is constant.
So N, the number of moles, is constant as well. Okay, now what happens when we take a constant mass of gas, same gas if you like, okay?
So the same number of moles?
Same number of moles. And now we are going to put some heat in here. We're going to heat it up. Okay, there's our flame. Now, the first thing we know is going to happen is that the
molecules are going to gain more kinetic energy.
They're going to be moving around much more. And they're also going to be banging up against the side of the container. Now, if this container is of a fixed size and we are increasing the temperature, what is happening to the pressure inside there?
The pressure is also increasing.
And Right, and we know this because of how we've defined our pressure is bang, 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 bang against the side. The more they move around, the more they bang against the side. There is another relationship here that we can look at. P proportional to T. Now there's just one little thing that we must say here, and that is that as we write these proportionalities, if I want to write pressure proportional to temperature, then I must use the scale of temperature at which the pressure will be 0 when the temperature is 0.
Yes.
Okay, so if I'm going to plot pressure against temperature, I must make sure that I'm using the scale which starts at 0. And that is the so-called Kelvin or absolute scale of temperature. And we must be careful about that. Now we know that that is degrees centigrade plus this figure of 273 is equal to K. Little point here, we don't talk about degrees Kelvin, we just talk about Kelvin. So when we take the centigrade scale, we add 273 and we get the reading on the Kelvin scale, and we know that on the Kelvin scale, this point at which the temperature is 0 and no pressure is exerted by a gas is called absolute zero. It's where molecules of gases and so on have no more kinetic energy. And so we can say this if we use the right temperature scale.